Most of us can picture a telescope, typically a long tube mounted on a tripod. Telescopes come in all shapes and sizes, and they're some of the most powerful machines in the world and in space. But how do they work? I'm Leilan from ESA Education, and today we're asking an ESA expert working on the James Webb Space Telescope. Welcome to our little studio.
Thank you very much.
Dr. Giovanna Giardino, thank you for being with us today.
Thank you for the opportunity. I'm very excited.
So what do you do at ESA?
So I'm an astronomer and I work for ESA on the Webb Space Telescope.
I think a lot of people envision a telescope like my childhood telescope, so it's sort of this tube. And even the Hubble Space Telescope is what everyone pictures as a telescope, this kind of giant tube in space. How does a telescope work?
So in very simple words, a telescope, it's a bit of a bucket of light, bucket of photons. So using a lens of a mirror that is inside this tube, you collect the photons, the light from an object and concentrate it, focus it in a specific point so that you have much more signal, much more light for that object that you would have with your naked eyes. And that way you can see far away objects, weak signals.
But then you have the James Webb Space Telescope that looks completely different, and yet it's still a telescope.
Sure.
Why does it have such a unique design?
The main elements of a telescope are really the mirrors or the lens that you use to collect the lights and focus it, right? So that's what you have to have. The tube is that we see in many telescopes that we use on the Earth as mainly two functions. One is the holding of the lenses, the lenses that you need, or the mirrors. So you have to have a structure that keeps them in the place and with the right distance from each other. That's very important for focusing. Going for the tube allows you to block off extra light from the surrounding that you don't want to come into the lenses and disturb the clear vision that you have on the sky. It also keeps it clean, right? In the environment every day there is dust and things, so the tube keeps it clean.
So the fact that James Webb Space Telescope doesn't have this giant tube, how is its structure being held together? How is it remaining clean?
Right. So the structure is held together. So by the primary mirror is mounted on the spacecraft, and then there is, if you notice, a tripod going off from the primary mirror to what we call the secondary mirror, right? And the lights gets into the primary mirror, the big bucket that I call, right? Get focused on the secondary mirror, and then focused again into the primary focus of the telescope where the instruments are, and we actually collect the lights and look at it in a camera or a spectrograph. So the camera, it's really a camera. So like the name says, we record images. So the telescope collects the light, focuses, and this camera collects it and records. So we see images, we can see the stars, nebulas. And the spectrograph, the light entering a spectrograph is dispersed with a prism, or we also use gratings, but the principle is the same. The idea is to disperse the lights and look at the components of the light. So like when you have invisible light and you shine it through a prism, you see the colors coming through. No, that's the spectra of the light. These are the components of the white light, the red, blue, yellow, that's the component. And the same we can do in the near infrared, and in the infrared, and we look at the components. And why do we do that?
Good question.
Yeah, because in a way, the lights that an object emits, it's a bit of the signature of the object. It tells us a lot of what the object is made of, which elements are present, what temperature, what the pressure, what the physical condition.
And then what about the famed honeycomb mirrors? Why is it a honeycomb? What's the structure?
Right. So as you know, the Webb Space Telescope is one of the largest telescope ever launched. It's 6.5 meters in diameter, the primary mirror. Even the primary mirror would not fit in any of the fairing of existing launchers. The diameter is about 3 meters. So the design has to be such that it could be folded for the launch to be fit into the rocket.
And I suppose the honeycomb structure is what really allows you to be able to fulfill that
Right, the honeycomb, so that you want a continuous surface, right? You don't want gaps. So the hexagonal, as the bees have discovered, it's a very efficient way to tile a surface and also give it a
bit of a round
rounded
structure.
shape. You could do that with squares, but then you end up with a square telescope, which is not ideal to focus the light.
So the honeycomb mirrors
Yes.
are not just in a honeycomb shape, but they're also this beautiful yellow gold color.
That's
what material are they made out of?
Each of them is covered by a very thin layer of gold.
And why gold?
Why gold? Because gold is the ideal reflector in the infrared. So for infrared, for a normal visible light, we often use silver or aluminium, right? It reflects very well in your mirror. Mm-hmm. But in the infrared light, gold performs better.
Okay. And that's sort of this
That's
outer
the surface.
surface layer.
The technology behind each of these hexagonal segments was developed especially for the Webb Space Telescope to make a large mirror that is light. So the material of beryllium was selected to make the structure that you see under the gold coating. And beryllium is very strong, very stiff. It's got good properties when you cool it down, it's stable, but at the same time it's a light material. So we could make a large telescope that is not too heavy and can be launched in space.
So you mentioned earlier a sunshield.
Yes.
Can we talk about the sort of structure of the sunshield as well and its purpose?
Yeah, the Sunshield is very crucial on this mission. It was very challenging to design such a huge sunshield, 5 layers of special material as big as a tennis court. So obviously will not fit in any of their existing rocket. Mm-hmm. So it was designed to be in a compact configuration and folded around the primary mirror at launch, so that it could fit in the fairing of the Ariane 5 rocket. And the reason it's there, it's because the Webb Space Telescope, it's optimized for observation in the near infrared, in the near and mid-infrared part of the electromagnetic spectrum.
That's the light that we can't see with our eyes.
Exactly. And that's the reason of the Sunshield, to keep the telescope and the instruments, the scientific instruments, always in the shade of the sun and the Earth. The space is very cold. It's minus 270 degrees. So by keeping the telescope always in the shade of the sun, we can cool it down to very low temperature, minus 220, 230 degrees Celsius, really cold. And that it's great to observe infrared light, because then we have a very sensitive instrument.
And how many detectors are on James Webb Space
So
Telescope?
there are 4 scientific instruments with different function for different type of science that you can do. NIRSPEC, the near-infrared spectrograph, MIRI, the mid-infrared instrument, NIRCam, the near-infrared camera, and NIRIS, imager and spectrograph.
Okay.
Yeah.
And what are you hoping that information will tell us about distant galaxies, just the early stars?
We see objects that are 13 billion light years away from us. We expect to detect these. So it means that we're going to see objects as they were 13 billion years ago. So these are the very young galaxies. So we want to know what was going on there. What was temperature? What was the pressure? How many stars? And we can do that with a spectrograph, exactly analyzing the light. And then learn how the galaxy form by looking at these very young galaxies. Yeah. If we come closer to home, we can also look, for instance, at the atmospheres of planets in our solar system, Jupiter, Saturn. Again with a spectrograph, learn what's going on these.
And Webb
planets.
will be looking at planets as well.
Yes, planets in our solar system, and also planets that we call exoplanets, which are planets that orbit stars in the galaxies.
Do you think James Webb Space Telescope will help us discover life on other planets?
That is a difficult question. Life per se, I think it will be difficult. I think it's not really something very likely. But because of this capability of looking at the atmosphere of exoplanets, and also, for instance, the moon of Jupiter's. I think we could learn a lot about whether the elements are present that could sustain life. So if we look at the planets, that it's what we call the habitable zone. So at the right distance from its own stars to have temperatures that are not crazy cold or crazy hot, right? So that's a temperature range that we think, okay, life could exist. And then we look at the atmospheres. And for instance, we see that there is oxygen, there is water vapor, there's methane. That could give us a hint that life is present or it's possible on that planet. So that's very exciting.
Wow, Giovanna, thank you. That was a lot of information, but I think it might be helpful if we went and saw the model of the James Webb Space Telescope.
Yeah, sure,
Should we do that?
Of course, let's do that.
Okay. Let's go take a look at this model.
Yes.
Wow. That is incredible.
Yeah.
Wow.
Yes.
It's quite impressive, even at this size.
It is. It's a very striking shape, right?
Giovanna, thank you so much for talking to us today.
It's been a pleasure.
It's really inspiring that a little girl who looked up at the stars in her hometown ended up working on the world's most powerful space telescope.
Yeah, it's very exciting and was very fortunate. Yeah.
Thank you so much.
Thank you. Thank you for the opportunity to talk to you.
If you're looking for more astronomy educational resources, check out ESA Education's Teach with Astronomy webpage and keep an eye out for more videos coming from ESA Education.